All right, so for section 7.2, we're going to start looking at how to find the volume of different shapes. And the way that we create these three-dimensional shapes is going to be a bit different in each of these section 7.2 lessons. But for today, we're going to be creating three-dimensional shapes using something called cross sections. So I'm going to go to GeoGebra and show you what that would look like. So here you have an example where this blue parabola here, this is the parabola x squared. And then this red line is square root of x. Okay, this will not always be this shape. This is just to give you an example. Okay, so you see this little purple line right here. That little purple line is called a cross section because it's kind of just like a slice of this area between these two curves. Okay, and I can take that purple line and I can kind of slide it, and you'll notice that the closer I get to the intersection point, that little line gets smaller, right? Kind of bigger here in the center, smaller on the sides, and you can see it over here in 3 dimensions. So I can turn this around, but there's your 2-dimensional graph shown in 3 dimensions. So let's take this purple line, and on top of that purple line, let's make a square. Okay, so this square here is called a cross section. So I took a purple vertical line and I drew a square kind of coming out of the page. So I can also take that square and move it around. So watch on the 3-dimensional side. See how the square is bigger in the center and then smaller on the ends? Well, the reason why it gets smaller is because, remember, squares have equal sides. So the length of this little purple line, the height of the square would be the same measurement, right? Because it has to be equal sides in order to be a square. Okay, so what I'm going to do is I'm basically going to take a bunch of little squares and I'm going to fill this space with a bunch of square cross sections. So let me actually go all the way to the end like this. And I'm going to fill a bunch of squares. So here's like, 6 or 7 squares. And obviously the more squares that I make, the more cross sections I make, this thing kind of turns into a 3-dimensional figure. I'm not exactly sure what you'd call this, but that's what it would look like. Okay? So let me back up a little bit. To find the volume of a shape that has cross sections like this, basically all we would want to do is we would find the area of each of these squares and then add up all these areas. But instead of finding the area of each square and adding them all up, because obviously that could get to be a bit cumbersome with as many squares as we would need, what we would do is we would use an integral, okay? Because an integral is an accumulation function, meaning that the integral, the action of applying an integral basically will add all these things up for you. So you would do the area of one square as a formula, and you would do the antiderivative to add them all up. Let's take a look at an example. First, real quick, on this slide, you're going to see area formulas. This is just to remind you how to find the area of certain shapes from geometry class. Okay, please keep in mind that my drawings are going to be a little rough because I am drawing 3-dimensional shapes in a 2-dimensional space. So bear with me. Find the volume of the solid whose base is bounded by the functions, the square root. So that's this line here is the square root. X equals 4 just tells me where to stop. And the x-axis, so that tells me down here that that's where we are cutting it. Each cross section is a square taken perpendicular to the x-axis. So you're going to run perpendicular to the x-axis and you are going to draw a square. So you can pick anywhere you'd like. This would be like our little slice, and then we build a square on top of it. Now again, this is not going to be real accurately drawn because I'm drawing a 3D figure in a 2D space, but remember that the height of the square would be the same as this distance measurement here. So if I draw a square over in this area, it would be a lot taller. Okay, but it's coming out of the page. All right, so let's start with this. Let's start with finding the area of one square. So the area of a square is usually just the side squared, one side measurement squared. If you look right here, one of the sides, this first little cut that we made, that distance is from the x-axis up to the curve. That would be the same as the y value of the curve, okay? The y value of the point on the curve. And remember, y values are determined by plugging an x into the equation for that curve. So the y value is equal to one side measurement, and the y value is equal to radical x in this problem. So we're going to plug that in for the side measurement. And that's going to give us an area of x squared. So the area of each square would be the x coordinate squared. So for example, this first one, the x coordinate is at about 1. Plug 1 in, 1 squared means that the area of this first square is 1 unit, about 1 unit. Okay, so to find the volume of this solid made by cross sections, we will be doing the antiderivative from 0 to 4 on the x-axis, and the equation for the area of each square, I just realized I put x squared, that would just be x. The area for each square is x, and then we are anti-deriving. So we're going to go antiderivative would be 1/2 x squared evaluated from 0 to 4. And we're going to plug in 4, plug in 0, though that won't really do anything. And then you're going to get an answer of, I think it would be 8. So the volume of the solid created by drawing squares would be 8 units.